So, have you ever run into what feels like a broken function in math? One that isn't invertible, one that, by all the rules, shouldn't even have an inverse? Well, today we are going to dive into the really clever mathematical trick that actually fixes them. All right, so here's a puzzle that might have bugged you in class. We're told over and over that a parabola fails the horizontal line test, and that means no inverse allowed. And yet, we use its inverse, the square root function, all the time. So what gives? How can both of those facts be true at the same time? It seems like a total paradox, right? The answer is surprisingly simple, and maybe a little ruthless. Sometimes you literally have to cut part of the graph away to save the rest. This one single idea is the key to this whole thing. Okay, let's dig into this. A mathematical paradox. Why some functions don't have an inverse. To really get it, we have to talk about the rule that's causing all this trouble in the first place. It's the horizontal line test, and you can think of it as the bouncer at the nightclub of invertible functions. So check this out. On the left, you've got a function like y equals x cubed. It's what we call one-to-one. Any horizontal line you draw only ever hits it once. Every output has its own unique input. But then, look at the parabola on the right, y equals x squared. This guy's got a problem. If I ask you, hey, what number when you square it gives you 4? You'd have to say, well, 2 works, but so does -2. You see? Two different inputs lead to the same output. That's a huge no-no for inverses. It fails the test. So, how do we fix this? This is where the magic happens. We use the cut strategy. Yep, we're basically going to perform a little mathematical surgery to force this function to behave itself and become one-to-one. And you know what? It's an incredibly simple two-step process. First, you find the exact spot where the function changes its mind and doubles back on itself. For a parabola, that's just its vertex. Second, you make a decision. You pick one side of that turning point and you just delete the other. That's it. The piece you're left with is now well-behaved. Okay, theory is great, but let's actually see how this works. Putting it into practice. We'll start with our old friend, the parabola, and then we'll work our way up to something a lot crazier, like a sine wave. All right, let's start with the classic. F of x equals x squared. We know its turning point, the vertex, is sitting right there at the origin, the point 0, 0. So that's our target. That's exactly where we need to make our cut. Now, just by a general agreement among mathematicians, we typically choose to keep the right-hand positive side of the graph. By simply making a new rule that says we'll only use x values of 0 or more, we've created a brand new, perfectly behaved function. And what's the inverse of this new function? You guessed it, the good old square root of x. And just like that, the paradox is solved. Okay, let's level up. Does this logic still work if the parabola has been shifted around? Let's take a look at g of x equals x minus 3 squared plus 1. The same strategy should still work, right? Yep, it absolutely does. We just have to find the new turning point. For this function, the vertex has moved from 0, 0 over to the point 3, 1. So that tells us our cut isn't at x equals 0 anymore. It has to be right at x equals 3. So we make the slice at x equals 3, we keep the right side, and now our new restricted domain is the interval from 3 all the way to infinity. And this new trimmed-down function is now perfectly invertible. Easy as that. Okay, now for the main event, taming the sine wave. I mean, this function is a complete mess when it comes to inverses. It's just this endless wave that fails the horizontal line test again and again and again. So how on earth do we apply our cut strategy to this? And this is where the power of this idea just becomes so clear. Mathematicians decided to slice out one very specific piece of the sine wave, the part that goes from negative pi over 2 to plus pi over 2. Why that chunk? Well, it's pretty brilliant. In that one little section, the function hits every single possible output value from -1 all the way to 1. It's one nice, continuous piece, and most importantly, this little slice passes the horizontal line test. And that specific, carefully chosen restriction is exactly how the arcsine x function is created. Now, this technique is super powerful, but there are a couple of common mistakes that can definitely trip you up. So let's go over them real quick to make sure you know what to look out for. Okay, the biggest mistake by far is cutting in the wrong place. Look over on the right side. If you cut the parabola at x equals 1 instead of at its vertex, that little piece between 0 and 1 is still there. The graph still doubles back on itself, so it still fails the test. You absolutely must make your cut right at the turning point. This second pitfall is thinking that the way we usually do it is the only way. Yeah, by convention, we keep the right side of the parabola. But what if we'd kept the left side instead, the part where x is less than or equal to 0? Well, that piece would also pass the horizontal line test. It's a totally valid choice. It just creates a different inverse function, the negative square root of x. So you might be thinking, okay, that's a neat trick, but why does this concept really matter? Well, because it's so much more than a trick. This is a foundational idea that unlocks whole fields of study, from physics all the way to the highest levels of math. Just think about throwing a ball. Its path is a parabola. Now, the math equation for that parabola works for negative time, but that makes zero sense in the real world. So physicists just restrict the domain. They only look at time t greater than or equal to 0. That makes the problem realistic, and it lets them invert the function to ask real questions like, at what time was the ball 50 feet high, without getting some bizarre negative time as an answer. And for anyone taking precalculus or calculus, this is absolutely essential. This is the fundamental idea that's used to define all of the inverse trig functions, arcsine, arccos, arctan. They literally couldn't exist without this concept. So mastering this now is a huge key to your future success in math.
So I'll leave you with this question to think about. We decided that the right half of the parabola, y equals x squared, gives us the inverse we all know, y equals square root of x. But what about that other half, the one we cut away? What does its inverse look like, and how does it connect to the one we already know? That's when you really start to understand the power of playing with these restrictions.